Welcome back to this NPTEL online certification course in molecular rearrangement and reactive intermediates. So in the last couple of classes I was talking about the carbocationic rearrangement. I talk about Wagner-Marvin shift in the last class. I talk about the pinnacle rearrangement. In the today's class my plan to talk about several other carbocationic rearrangement. So let's start today's class with the contents I am going to cover for today. So I am going to start with the semi-pinnacle rearrangement, and I am going to show you what is the importance of semi-pinnacle rearrangement, and then I am going to talk about the Tiffany-Demjanov rearrangement. I am going to talk about the Mayer-Squist rearrangement, then the Beer-Villiger rearrangement. So in the last class, if you remember, I was talking about the pinnacle-pinnacle, and always I try to tell you that the carbocation going to form there, which will be more stable. That means if you have a two different place you have alcohols, then the water elimination is happening where your more stable carbocation is generating. But now suppose from this particular compound, if I want to get to this particular compounds. So if you try to look into this problem, first thing is, okay, you have a vicinal diol, you might think, oh sir, what about putting acid? As soon as you put acid, you will generate a more stable carbocation here. From there, what is going to happen? There might be a 1, 2, so there is 2 hydrogen here, so there will be only possibility of hydride shift. It can generate little bit of aldehyde. And then the other way that there is you can generate this particular carbocation, which will be highly unstable, so it will drive the reaction towards the more stable carbocation. So now you cannot able to form this particular compound through this method. So now the idea is that how to selectively form a primary carbocation, means how to selectively get rid of this OH to make a carbocation on this particular carbon. If you can able to make the carbocation very easily, then there will be a 1,2 shift which I have mentioned here, which can give it to your target product. So that is going to bring you to the semi-pinnacle rearrangement, where the idea is you try to convert this OH to a leaving group. Selectively you have to convert this primary alcohol to the leaving group. That will allow this 1,2 shift happening to the corresponding desired product you want. So this can be done using this pyridine tosyl chloride. Now if you use tosyl chloride and pyridine, I think you guys already know about this form these acylating agents. Pyridine react with this tosyl chloride. So now what is happening, if you use this tosyl chloride with this diol, this vicinal diol, this is a tertiary, this is a primary. So primary will form very fast, this this product will be obtained. So now once you have this particular compound, once you treat with this calcium carbonate, so in absence of any acid, this will go for this 1,2 shift, it will giving to these particular compounds. Okay. So this is the beginning of the semi-pinnacle rearrangement, and there are lot more example. I am going to bring some of them here. Again there is a scenario here where you have a tertiary alcohol versus a secondary. So previous slide you have a tertiary versus primary, here tertiary versus secondary. Again if you use this tosyl chloride pyridine, it will form selectively in the secondary. Again the major is the steric effect. Due to steric, it will go to the primary or secondary, not the other hydroxy group. Now once you treat with the calcium carbonate, is going to go for this ring expansion. Now there is an important thing here. In this particular stage, there is two different places can be get expanded. It can expanded through this side where you have this alkyl chain, or it can go through this side where you have this vinyl group. Now again I told you this expansion of this 1,2 shift, wherever groups is going for 1,2 shift, we will have some sort of a delta positive, and this vinyl group able to stabilize the delta positive more compared to this alkyl, that allow you to get the vinyl group to so this part of this ring will participate in this 1,2 shift, that will allow formation of this product. Okay. Again there is another example here. If you have this primary iodo compounds, in place of silver nitrate, it can form this corresponding positive charge that will allow this 1,2 shift here to form this particular compound through semi-pinnacle rearrangement. You might find in the exam or in the practice question that in the same compounds, if you use a pinnacle rearrangement, you will get one product. If you use semi-pinnacle rearrangement, you will end up getting other product. There is another example here. So this is a epoxide. I told you before that if you treat epoxide with a Lewis acid, BF3 thread, what is happening here? There is formation of a delta positive charge in this carbon, or there is a carbocation formation happening in this carbon. So that will allowing this ethyl shift here. So this is coming here, ethyl group is migrating here, forming this compound. You might be asking this question, sir, why this is ethyl shift is happening, why not this alkyl shift? Now the question is, once you go for a alkyl shift, what is happening? As soon as you go for a alkyl shift here, instead of going for, then you will have a ethyl and a OH, which will be a ketone. But the major problem what you are going to encounter here, you are making a 4-member ring from a 5-member ring. So that is not going to be a favor, you are making more strained ring. That is why this is not going to happen, the reaction will go through this pathway. So this is about the semi-pinnacle. Again, there are more example for you to practice. So then we are going to introduce this Tiffany-Demjan of rearrangement. Again, the idea is same, very similar to the semi-pinnacle, but the idea is you are using a different approach to generate this carbocation. So this reaction was discovered by this Russian chemist, the Nikolai Devenabov. He discovered this reaction at 1901. So what is happening, that now instead of this 1,2-vicinal diol, you have this amino alcohol. Once amino alcohol treat with the HNO2, it forms the corresponding diazone compounds here, and now there is a N2 getting released to form this corresponding carbocation. And now if there is a carbocation, and now it is very similar to the pinnacle, and you guys have already learned about that in the previous lecture. So that will allow this one to shift happening from here to here to get to this corresponding product. Again, from amino alcohol you are ending up getting to the corresponding carbonyl compound. So this is the end product. So now we are going to learn some of the example. So here I am going to show you some of these example in terms of ring contraction or ring expansion. First thing is, if you have this type of amino alcohol where this NH2 group is attached with a CH2 group and that is not attached in the ring. In that case, what we observe? We observe ring expansion. What is happening? First it forms the N2 plus, that will get rid of N2, formation of carbocation, and allow this ring expansion to happen to form this cyclohexanone. Now if it is happening that both hydroxy and amine is actually the substitution in the ring, then what is going to happen? In that case you will form the N2, so that will eliminate so there will be minus N2 to generate a carbocation, that will allow a ring contraction to form this particular product. Okay. So that means if you want to go for ring expansion versus ring contraction, you can use this technique as well. There is another example of ring expansion where you can see this is not in the ring substituted. So this is CH2 NH2 which can form this N2 plus. Now it will allow this one to shift here to form this expansion product. And again here there is a two possibility. Here you can expand, the ring can be expanded through this or through this. Now which side it will go? It is going through this side because the case is you have this side, you have this vinylic group. So that is going to stabilize the carbocation, and that has a migrating aptitude will be higher. So that is why you end up forming this particular product. Okay, so now I am going to talk about this particular rearrangement, Tiffany-Demjan rearrangement, with a example of a cyclohexane where you have a terbutyl group here in this position, and then you have amino alcohol. So this can end up forming. So if you put this terbutyl group in the equatorial position, you lock the particular conformation. Now you have 4 different diastereomer here. There is 2 here and 2 here. So now these 4 different diastereomeric amino alcohol, once treated with Na2 and HCl, it will end up forming different products. So now we are trying to understand what is happening, why they are forming different products here. First thing, we know that once we use this HNO2, it will form this N2 plus. So the most important thing is, once you form N2 plus, which groups is going to get migrate? As I said, this migration is going to happen only if you put sigma star. So there is a sigma star orbital and there is this sigma bond which is going to migrate. So this sigma and sigma star has to be anti-periplanar. So this anti-periplanar arrangement is very important, because only then it is possible that the sigma can give electron to this sigma star orbital. And then what is going to happen once this migration is happening? Now you can, this OH can give lone pair to form this corresponding aldehyde. So both of these compounds that can end up making to the same product, because in both the cases there is a possibility of this sigma to sigma star donation, and so this sigma going to shift here to form this product. Once we start with the other set of compounds, the other set of diastereomer, what is going to happen here? Again, first thing is this amine going to form the N2. Now once this form M2, now you can see you have this sigma star here. So that is your sigma star, and if you think about anything anti-periplanar to that, then only this hydrogen is ready here, this CH bond. So now what is going to happen, instead of this sigma bond donation, this CH bond going to give electron density here, which end up forming these corresponding carbonyl compounds. But in other cases, if you have both are diaxial, then what is going to happen? It's going to form this N2. That means now in this sigma star orbital, this oxygen lone pair can give electron density here, that can form this corresponding epoxide. So that means you can see that the logic remains same, that you have to find out which group are oriented in the anti-periplanar fashion. That group or that sigma bond can only participate, or there is a hydrogen, it can participate there to give the sigma bond of this CH sigma bond electron cloud, or if there is a oxygen, which can give this lone pair to form this corresponding epoxide. So now I am going to move it to another important reaction called Myers-Koester rearrangement. So this is another reaction where this carbocation is forming in the propargylic alcohol. So if you start with a propargylic alcohol, which is secondary or tertiary, so this alcohol can be a secondary or tertiary. Once you treat this with acid, what is going to happen? It can form the alpha beta unsaturated carbonyl compound. So this alpha beta unsaturated carbonyl compound will form. So how it is happening? It first forming this particular carbocation after elimination of water. Now it will go for a resonance to form this allynyl carbocation, which will attack by water. Now it will going to form this corresponding alpha beta unsaturated ketones. So let us go through some of the example here. So this is one example here, where this is a particular case. We can see this is a propargylic alcohol, which will form, which will get protonated, then it will going to form this allyne, and once you form allyne, it will going to get attacked with this water, which will form these particular compounds. Once it will form that, there it can be do further transformations to get to the corresponding natural products. There is another example here. We have another propargylic alcohol here, you can see. Now here also you can see you can form this corresponding carbocation. Now you can see there is this type of allynyl carbocation will form, but here we have a OAT group. So the water is going to attack here, and which is going to end up forming a ester. That means depending on the substitution here, you can end up making corresponding ketone or corresponding ester. So now I am going to move it to another very important reaction called Baeyer-Villiger oxidation or Baeyer-Villiger rearrangement. This reaction was discovered by Adolf Bohn Baeyer and Victor Villiger. They discovered this reaction that if you take a carbonyl compound, treat with peroxy acid or peroxide as an oxidant, it will allow to formation of the corresponding esters. So let us try to understand this reaction, that what is the mechanism of this reaction. First thing is the protonation. After the protonation, this compound getting attack here to formation of this intermediate, which is called the Craigie intermediate. After that, what is happening? After that, there is a protonation happening in this position here. Then there is a most importantly this 1,2 shift. So this group is which attached to this carbon getting migrated from this particular carbon to corresponding, where it is happening, it migrating to the corresponding oxygen. So there is a carbon to oxygen migration happening, 1,2 migration is happening, which finally end up you giving to the corresponding ester. So first we are going to learn a couple of things about this reaction. First we are going to learn the primary stereolytic effect. We are going to learn the secondary stereolytic effect. We are going to learn about what will be the migrating ability of the groups, and then the steric effect of the groups as well. So let us start with the primary stereoelectronic effect. So let us try to understand this reaction into the little bit with the orbital picture. So what is happening here? So one important thing this reaction is that when this reaction is happening, this oxygen bond and in the peroxide and the group going to get migrate has to be anti-periplanar. So this anti-periplanar thing is very important. What is mean by that? It is saying that these particular things here, this oxygen and this particular migrating group, you can see they are literally are actually anti-periplanar orientation. So if it is anti periplanar, then what is going to happen? Then this sigma bond electron density of this migrating group which is attached with this carbon going to get transferred the sigma electron to this sigma star orbital of this oxygen. So that will allow this 1,2 migration to take place. We can see from this also that they have to orient such a way that this sigma star orbital can be accessed from this sigma orbital which is here. So this is called a anti-periplanar orientation. So this is about the primary stimulating effect. What about the secondary? So there is another important thing that after formation of this alcohol, so this alcohol also do some important role here. So alcohol has a lone pair, so now alcohol lone pair can give electron density to this sigma star orbital. So there is a sigma star orbital of this migrating group. So this migrating group also have a sigma star orbital which is this, now receiving electron density from this lone pair or the non-bonding orbital from the oxygen. So that electron donation can also going to help you this reaction. So again we are said that they have to be oriented such a way so that this is possible, so that so that the oxygen now can able to oxygen lone pair can able to give to this sigma star orbital which is oriented here. That is the sigma star orbital of this bond, and there is this lone pair which can able to donate. This is called the secondary effect. And now we are going to answer the another very important question, that what will be the the migrating aptitudes for different groups. So there is two important thing, one is the stereoelectronic effect, another is the steric effect. So what is happening, you are breaking this corresponding sigma bond here, and which is going to give electron to this sigma star. So in the transient state what is happening, this it is forming again this this there are 3 orbital and 2 electron bond formation happening here. You can see this is 3 center 2 electron bonds here. So there is a partial positive charge on the carbon which is getting migrating. I put here this tarbutyl group here. If the tarbutyl group is migrating, there is a bond breaking happening when this group is getting migrated. So this is going to carry a delta positive charge. That means which group can stabilize the delta positive charge more, that can have a more migrating capacity, more migrating aptitude. Okay. But there is also some steric effect, that is also important. Sometimes the steric effect also predominate over the electronic effect. In general, so there are, it's very difficult to generalize, but in most of the cases these are the order followed, but there are also some cases when the order change based on the different other effect as well. So let's start with this simple example here. If we have different type of acetophenone derivatives. Here we are changing different group in this acetophenone from we are going from methyl to ethyl to isopropyl to tarbutyl. So what we are increasing in one side we are increasing the steric effect, we are increasing their size. Other side we have a phenyl. So once it is forming this corresponding Krege intermediate, now there is two possibility. Either the phenyl can migrate here or the R group can migrate here, which is here. So that can form this particular product. If phenyl migrate, it will form this product. So what we observe that once R equal to methyl, we are seeing 90% yield of phenyl migration, almost 90%. So I think there is 0, either there will be 10 or this number will be 100. And then there is a 87:6. So what is happening that if you have ethyl, if you have a propyl, butyl, slowly what is happening, this value is getting decreased, and slowly we are seeing this value is getting increased. So once you come to a tarbutyl group, now tarbutyl is a better migrating aptitude compared to a phenyl. Okay. So we know that phenyl can, the benzylic things can stabilize, the phenyl can stabilize the corresponding charge, but again the tarbutyl is getting migrated, okay, instead of phenyl here. So here, so that means the steric is also playing important role here. Now if you have a chiral center here, does the chiral center remain same, there is a retention happen or inversion happen? What is actually happening, there is a chiral center remain retention, there is no change happen on this chiral center, because if you see here in this intermediate, there is nothing happening in the chiral center, only thing this bond is getting broken and it is migrating here, which you can see from this particular tangent state. So that means in the final product also you see this, the configuration remains same what you started with. So you can see some example here that the configuration remain same as you started with. Okay. So here some of the example here, that if you treat with MCPBA this compound, what is happening, there is two different possibility. Once you make this Krege intermediate here, now you have to think about what are the two different site. which side can again stabilize the carbocation more. We can clearly see this will be the winner having a secondary versus a primary, so it will form this product. Again I talk about this product here, you have a methyl one side, you have a benzylic another side. So if you have a benzylic, then the benzylic will have a better migrating aptitude because the benzylic carbocation will be get more stabilized. Again if you have a CF3 one side and this you don't have a electron withdrawing group on the other side, then the side which you don't have electron withdrawing group will be the winner forming this particular product. We have learned about this, that if you have a methyl versus phenyl, then you can end up here once you put a NaOH, this can goes to corresponding phenol. So this is a very important thing, that how do you convert acetophenone to phenol in one shot. Okay. Again the phenyl is a better than CH3. Again we have an example here, methyl versus cyclohexyl, again the cyclohexyl is the winner. And we have shown you that if you have a phenyl versus tarbutyl, then the tarbutyl migrate first, then compared to the phenyl, so there will be oxygen here. And then there are some other example here. You can see there is a two possibility on this particular carbon, because now once you attack with the paracet, now this side can be migrated or this side can be migrated. Now this is a secondary, so there is a major possibility of this side getting migrated to forming this product. So once you are trying to solve this thing problem in the exam, you should look into this. Again there is a very similar scenario here, there is a secondary versus a primary scenario. The secondary is getting winner to form these particular compounds here. Okay. So that means what is happening, that we have to, when you are trying to understand this type of reactions, try to think about that in the Kriege intermediate, which particular side has a more possibility to migrate. That will migrate first. Okay. As I said you that reaction not only done with MCPBA, I told you at the beginning you can use H2O2 and acetic acid. That also do the job well. Okay. Now we come back to so this is a very important example here. So after this is getting attacked and this is forming this corresponding Kriege intermediate with MCPBA, what is happening now? You can think about there are two different side here. Okay. So you can migrate from this side or you can migrate from this side. Okay. So what we are observing here, that the migration happening from this side only. So this is because you can see this is a tertiary carbon to migrate versus this will be a primary carbon to migrate. That is why what is happening, that is ending up to this particular product. Okay. And now we have a scenario where you have a electron deficient phenyl and there is and that is only phenyl. So if you have a only phenyl versus electron deficient one, what is going to happen? There is one which is electronically deficient cannot migrate, because I told you that there will be a delta positive charge. So that delta positive charge cannot get stabilized with that. So that is why you will observe that the phenyl group is going to get migrate here to form these compounds. And then there will be another very important example here. So these are the example which is applied for synthesis of very important molecule. So I try to bring this example here because you might find similar questions in your exams or in your practice question as well. So once you try to see there is MCPBA is given into the problem, now you try to look for that what you have learned from MCPBA, that if you have a double bond in the compound, it will form epoxide. That is we know. Suppose you don't have a double bond here in this molecule, correct? We cannot see a double bond here. So that means what is the possibility here? If you don't have a double bond, then you look for a carbonyl group there. If you have a carbonyl group, then we know that MCPBA is going to get protonate, then going to get attacked. But now once it is getting attacked, it has a possibility that which side is going to get migrated, this side or this side. Because we know that if it is going to migrate from this side, it will going to form a completely different product versus if it migrate from the other side. Okay, because that that connection will be completely different. So you can see there the what is happening. We end up seeing the migration happening from this side, not from this side, because you have two chlorine which are electron withdrawing. That is why it is going to form these particular compounds, and after several steps it can form these particular compounds. There is other example here. You have this example here. You have one carbonyl group here, one MCPBA attacked. This is comparatively easy here because you have a methyl versus a cyclohexyl, and we all know that the cyclohexyls will have a better migrating group compared to a methyl group. And then after that it can form this the CD ring of the taxols. So now I am going to talk about another important rearrangement reaction called Beckmann rearrangement. So what is happening in the Beckmann rearrangement? In the before that I am going to talk about, this was discovered by Ernest Otto Beckmann, discovered these reactions. So what is happening here? Once you treat with this carbonyl compound with hydroxylamine, okay, then the oxime functional group to substituted amide. So from oxime is forming oxime, which is going to convert to corresponding substituted amides. Okay. So this is a very important reaction. That reaction has a lot of importance, because not only it goes to amide, if you have a cyclic oxime, it forms corresponding lactams, okay, and it often catalyzed by acid. You can see it often we use acid, but there are also examples where we use sometimes in tosyl chloride, thionyl chloride and other things as well. So what is happening? First step is the protonation of this. Once the first thing, your formation of this corresponding compound, once you form this, now what is going to happen? The acid going to get protonate, release of water, allow this 1 to shift. So now the important thing is this 1 to shift happen only there in the trans position. They only participate in this 1 to shift to form this corresponding nitrilium ion. Once you form this nitrilium ion, the water attacks here, which finally goes to the corresponding amide. And if you have a cyclic one, then you end up making to this very important compound here, okay, which can apply to the to the polymer industry. So now in case of intramolecular also is forming this. After forming this, it can protonate it. After the protonation, what is going to happen is going to goes to the corresponding nitrilium, and then water attacks to the corresponding product. Here are some example. What I am going to show here, that after the oxime formation here, that is very important, that if you are forming oxime and these two groups are not very different in the size. If they are different in the size, there is a possibility of formation of particular oxime. But if it is not very much comparable, then they makes a 3:1 ratio. But once you treat for the Beckmann rearrangement, it end up the corresponding amide in the same ratio as well. What I am trying to mean that it does not matter what oxime you form. Once you form this oxime, it will going to get this methyl going to migrate, because the one which is trans to that alcohol is only going to get migrate. Okay. So that means here the corresponding the ethyl going to get migrate in this case, and here you have a corresponding methyl going to get migrate. We have an example here. We are showing here intramolecular example where it can goes for this formation of this corresponding compounds which can attack with the water. So corresponding nitrilium which get attack with water to corresponding amide here. There is some other example I am going to show you. So you should look for here. In the previous case, you look for primary versus secondary versus tertiary. Here you look for which one is trans to it. Here this particular skeleton is trans to it. That's why this side is getting expanded, okay, to forming this corresponding product. Again you can see here this group is trans to it, not this one. So if this is the trans to it, this is going to get migrated to forming this product. Here you have a scenario here that you form this corresponding oxime. Now you have a two different scenario. You have it can migrate from this side, or it can migrate from this side. So what you observe that it is getting migrated from this side, which is trans to it. So you have to understand that trans side only getting migrated, not the secondary versus primary. You cannot compare that. Okay. So that's all about the Beckmann rearrangement. So I think we have learned very important thing. We have learned the semi-pinnacle rearrangement here. We have learned about the Tikhonov-Demjanov rearrangement. We have learned about the Myers-Coester rearrangement. We have learned about the Baeyer-Villiger, and finally the Beckmann rearrangement. So these are very important topic. There are these reference book. You can go through the Claydon and Karisenberg and other books. Thank you all, and thank you for listening. I am going to see you guys in the next class.